Good. So good morning. I am Philippe Piot. Um, uh, Thank you for joining the BeamNetUS Town Hall. The purpose is to showcase the program and take any question. Toward the end of this meeting, you will have an opportunity to join the breakout room to discuss with staff from a specific facility you might be interested in. So, yeah, BeamNet US is a consortium of facility that was established about a year ago. And this is currently relying on or based on DOE Accelerator Test Facility. The National Lab in the US has a comprehensive ecosystem of state-of-the-art facilities. There are facilities that span a wide range of beam energy, particle species, parameter, and therefore can support a broad research program. They also have expert staff in accelerator science and engineering. And some facility have some special resource, such as very high power laser system or radio frequency test stands. And one thing that was realized over the years is that very few of these facility, I think two or three, are users facility. And most of them, they have a model where you can use Beam on a collaborative basis. And so BeamNet US is kind of providing a platform to streamline this access through collaboration through these facilities which have a partnership-based model. So right now, BeamNet US has six national lab taking part of in the program and 12 facilities. These facilities are united in a common mission to advance accelerator research and breakthrough application, to democratize access to cutting-edge accelerator facility, and to foster cross-community collaboration and innovation. And of course, there is also a workforce component, workforce development component, which is to build the next generation of accelerator experts. So this facility, they offer a broad R&D opportunities. Again, they have a unique set of distributed capabilities. We have electron, positron, ions, and proton source available throughout this facility. The particle energy range from a few hundred keV to several GeV. We have access to 100 terawatt lasers, to high power RF test stand and source and for testing, and to advanced particle and radiation diagnostics. So this facility can provide a large range of opportunity for your research, and they are again supported by expert operators and accelerator scientists. So these are examples of topics that have been proposed or considered for the BeamNet US program. So we have access to polarized beam. So this can support some nuclear physics related topics. The facility by themselves can support beam physics, control and diagnostics, and an important aspect of that is application of machine learning to control beams and beam distribution. There is also some facility that uses plasmas, and this provides opportunity for studying novel particle acceleration, a new radiation source, or laboratory astrophysics. A couple of facilities have high power radio frequency test stand, and again, this provides an opportunity to test new cavities or how material behave in high electric fields. And then a lot of this facility, of course, they generate radiation, and this has application in for irradiation purpose in medicine, also in this single effect SE for electronic and microelectronic application. And finally, some of these facilities provide electron beams that can serve as a quantum probe, and this is used in ultrafast electron diffraction. We have a couple of facilities that can do that, and also study chemical dynamics and other things. So the BeamNet core mission is to coordinate the outreach effort and web resource to publicize the capability of member facilities and the opportunities for participation. It's also provide a point of entry for users, especially from academia and industry, who are not already part of the established user collaborator community. And also, BeamNet US offer a streamlined proposal process for gaining access to member test facilities. Ultimately, BeamTime is awarded to perform an experiment on a specific facility, and also the award goes to the PI that proposed the experiment. The monetary support goes to the facility which is hosting the experiment. And this is to have a cost recovery for beam time and staff support. And one can also, and this is something you should discuss if you are interested with the facility you are looking at applying for beam time. This financial support can also support travel and maybe some minor material and supply costs. But again, this has to be worked out with the host facility. Um, as I said, in FY25, we were in a pilot year, and this year we kind of started to have a more organized organization. And I think the major addition was the addition of Lottie, who is in charge of outreach and user engagement. And that's something that was missing. We did not have a technical person in FY25 that could spend a significant amount of their time to promote the BeamNetUS program and also understand the portfolio of facility in the program. And then Emma and myself are co-sharing the BeamNetUS program. And then we have support from Mary-Jane Lardy from Brookhaven in terms of administration and also outreach. And as I said, we have an external review committee that review all the proposal that you will submit, and the proposal will be continue to be shared by Patrick Mugli from Max Planck Institute in Munich. So let me say a few words about the proposal and beam time allocation process. So the proposal, the call for proposal were out about a week ago. And what we expect or encourage a proposer to do is first connect with the facility, point of contact, and discuss a possible experiment plan and their compatibility with the facilities they are considering. And we have an updated user handbook that I advise you to look through about the process, but also about capability of the facilities. Then by November, by the end of November, you will proposal submission window is closing. And so the proposal process is that, again, the proposal are shared with the selection committee, proposal selection committee panel, shared by Patrick, and they are reviewed based on their intellectual merit and broader impact. And then the highest ranked proposal are awarded experimental time, again, subject to a feasibility report by the facility. And we require the proposal to include a statement, or maybe it's just a check mark that the PI have already discussed with the targeted facility to make sure that their proposal is consistent in terms of technical feasibility, but also schedule or needed beam time. And then once the proposal are awarded, which we believe will be early 2026, then the successful applicant will have about 9 months or so to finish the planning of their experiment, to schedule the experiment, and then perform their experiment as a selected facility. We do not have yet this settled, but usually we have a reporting requirement where we have small PI meetings, and we will send or share more information once we have uh, settled this aspect of the program. So if I showcase what we had for FY25, we awarded 8 proposals on 8 different facilities. The submitted proposals span material science, radiation therapy, laboratory astrophysics, photon science, plasma physics, beam diagnostics and control, including machine learning and beam physics. And these are the proposals that were awarded. So they are color-coded according to the field. So I think 2 were related to photon source R&D. 3 were related to beam diagnostics and control. And a couple, one was related to material science, and one was in between material science and diagnostics. And finally, one was related to plasma physics. And these are actually examples of 2 experiments that were completed a few weeks ago now. And I like both of these experiments because they showcase exactly one of the critical aspects of BeamNetUS, which is to attract non-traditional users. In this case, for instance, the NSCT experiment included a team of students that were doing this as part of their thesis project at Harvey Mudd College. An institution which is, traditionally not an institution taking beam time at the accelerator test facility. And likewise at AWA, the user or the collaborator was a PI from Resselner Polytechnic Institute, which is again a non-traditional user of test accelerator. So in summary, BeamNetUS offer a world-leading and unique opportunity for your research to access accelerator test facility. I think the pilot experiment so far was a success because the program started late in the year. It turned out the user had only about 6 months to plan their experiment. So this led to some experiment being delayed and not yet completed, but I'm confident this will happen soon. And the program is growing. The FY26 development include 3 new facilities that were added. And I think most importantly, Lotte, who will dedicate half of our time on outreach and user engagement. So we would like to, continue growing our network, and this rely on an active participation from the community. So subscribe to our mailing list and follow us on LinkedIn. And I think that's all I had. So let's say I'm just on time. Lotte, since you are running the show, we have time for a question, or we should move
Yeah,
on?
sure. I think we can take a question or two if there are any. Otherwise, we'll have a longer Q&A at the end around 10 o'clock. So people can either ask questions now or they can hold on to the questions to the end, whatever they prefer.
Mhm.
Seems like there's no
Uh,
questions now.
I
Or Mike, did you have a question?
Yeah, just a quick one. Is the scope of these projects 1 year, or um, uh, does if one envisions a 2 to 3 year project scope, would one just renew each year, or do that at the outset?
I'll answer, and maybe Emma or Lotte can add. So nominally they are 1 year proposal, but because they include the review process, usually it means that you only have maybe 9 months, or we hope eventually more if we kind of shift the proposal submission window. But so right now they are more like a 9 months project to complete the experiment.
Hmm.
So 1 year if you include the preparation of the proposal.
Okay.
they are not renewable. And the idea is really that this should be a seed to start a collaboration and then
Mm-hmm.
go to other program. And so, a typical success story would be somebody that comes with an idea, uh, do a sanity check and some preliminary experiment at the facility, and then go with that to a funding agency and get, something of a larger scale funded over multiple years.
Yeah. Okay, thanks.
Maybe if I just add one thing, Philippe, we don't have a restriction in place that restricts previous users from coming back. So essentially, you could just submit a follow-on proposal the following year, and then it's up to the PRP to decide for the criteria that we mentioned, if it's merit and impact are sufficient to sort of like support continuation of that project.
Right. Okay.
I have a quick question too.
Go ahead.
How long is each campaign? Like, how long is the time slot?
So I think last year, we most of the facility with the funding they had and their program already. I mean, most of these facilities support other programs. They had about between 1 to 2 weeks of beam time allocated, and then maybe an extra 1 week for related installation and disinstallation of experiments.
Okay, thank you.
Any more questions at the moment? Okay, in that case, we can move on, and I will share my screen.
Sorry to interrupt. There was one
Go
question
ahead.
in chat, but this might be a good one to save for the Q&A session at the end.
So the question in the chat is, for such seed funding scenario, is the review process criteria the same or the same as the same more regular proposal? Yeah, maybe indeed we could follow up in
Yeah,
the
or
Q&A.
in the Q&A, yeah.
Okay. Okay, I'm going to share my screen now. Okay, so I am just going to step with you through the process of submitting a proposal. You will navigate to beamnetus.org/access, and then you will see this page, which I hope you see. Philippe, can you confirm that you see my screen? Awesome.
Yeah.
Okay. And then you will see essentially the facilities that are currently accepting BeamNetUS proposals listed here, as well as some key dates that Philippe already alluded to in his presentation. November 30th is the proposal deadline. And then you can see these 3 buttons here. And then I would recommend to first go to the submission portal, which to get an overview of the situation of the submission process. This is a Google form. So you do need a Google account to use it. In the past, this has not posed any restrictions for users to submit their proposals because apparently everybody has a Google account. If this does prove prohibitive for you, please do reach out and then we can find another way for you to submit your proposal. So this form essentially collects your key information, but it also provides a link to our proposal template, which is a docx document that you can download and modify. I can show you that later. And you will need to then upload that form at the end of, or this document at the end of the form. It also links to our user handbook, which Philippe also mentioned in his talk, which is really useful to give all kinds of information about the proposal process, what the review criteria are, what the detailed steps are, etc. So I do recommend looking at that if you have any questions, and then of course you can reach out to us as well. So this will collect your name, your email address, your institution. You will be able to pick a first choice facility. This is going to be the facility that will be essentially the main facility that you write your proposal for. You have the option, but it's not needed to select a second choice facility. So in the case that your proposal cannot be accepted because your first choice facility is already fully booked, but your proposal ranks high enough to be accepted into your second choice facility, then we will reach out to you and see if you want to transfer your proposal to that second choice facility. And then finally, you'll need to confirm with this check mark that you have indeed reached out to the facility POC to discuss the feasibility of your proposal project. This is also something that Philippe mentioned in his talk. You can find the contacts of all our facility POCs on the facility pages on our website. Down here, it lists the point of contact with email addresses linked so you can get in touch quite easily to discuss your project. And then finally, you will be queued to submit your completed proposal, which is that document that I mentioned in the beginning. So this is a document that we recommend to download, but you can also modify it in Google Docs if you have a Google account. It essentially gives you all the necessary sections that you need to fill out, including some descriptions and Q questions that you might want to answer in these sections to submit a proposal that has a good chance for in the review process. It also provides some character limits and a maximum page size, a page length. So please make sure to adhere to these limits. You will then save this as a PDF and then you will upload this at the end of this form. So as I mentioned before, do look at the BeamNetUS handbook if you have questions. There's also an FAQ at the end of this beamnetus.org/access site. So you can go here if you have questions, but do reach out to us and you can find all our contacts in the handbook at the end of this document in case there are questions. So please feel free to reach out anytime. Please also subscribe to our mailing list if you haven't done so yet. So if you go to the bottom here, and you click this, then you'll be directed to the Contact Us form, which you can also use to reach out to us. But importantly, there's the subscribe field here where you can sign up to our mailing list, as well as linking to our LinkedIn page. If you're on LinkedIn, then please follow our page so that you can stay up to date easily with what's going on with the network. This is all I had for the proposal submission process, and then I can stop share, and maybe if there's a question now, we can discuss that. Otherwise, I can hand over to Emma as well. I don't see any questions. So Emma, do you want to take it away?
Sure. Okay, so now we're going to have presentations from each of the facilities. So I'm going to share the slides and then advance the slides through each facility. Please hold your questions to the end. We'll have a group Q&A session at the end of these facility presentations, and then we'll split up into breakout rooms if you have specific questions about the process at a particular national lab or one of these facilities. Okay, so we are going to start with the UED facility at Brookhaven National Laboratory with a presentation by William Lee.
All right, thank you. Yes, I'm William Lee from the Low Energy Accelerator Development Facility at Brookhaven National Lab. We're kind of transitioning from the UED name to this LEAD name because we're adding a capability that I'll go over in a bit. So LEAD encompasses both the ultrafast electron diffraction beamline, which provides ultrafast mega electron volt class electron beams at high repetition rates. You can see a table of the typical beam parameters on the right. I won't go into this in detail, but to sum up, the beam has high repetition rate, about 3 mega electron volt energy, fairly low charge, but ultra fast and high quality electron beams. There's a synchronized Ti-Sapphire laser. Can you go back, please? There's a synchronized Ti-Sapphire laser to do pump probe experiments for diffraction, and we are also in the middle of building a beamline extension for single event effect testing for electronics. Additionally, we've just added some accelerator science and technology radiation shielded bunkers. These are basically big shielded bunkers that are meant to be a flexible space for a broad range of accelerator research and development activities. We'll provide RF power, electrical, cooling, etc. for testing users' accelerator equipment. Next slide, please. So this is a little overview of both parts of the facility. On the left, we have UED. So we have a little schematic of the beamline. It's a fairly simple beamline consisting of just the RF electron gun, solenoid lens, sample chamber, and a detector. Currently, on the right, you can see the planned extension, which adds another sample chamber and some more diagnostics. So UED is really designed for experiments that study ultrafast dynamics of materials, such as thermoelectrics, superionics, and phase-changing metamaterials. With the new extension, we can also support single event effect testing and samples with worse vacuum compatibility. In addition, machine learning development has been done at this facility. The AES&T bunkers consist of two fairly large bunkers, which again are radiation shielded and are meant to support testing of new accelerator equipment. And here on the right box, you can see the experiments that are currently scheduled for these bunkers. So some common attributes of experiments at LEED. So LEED staff can assist with experimental design and technical and engineering support. Ideal experiments at UED include material science experiments, or really any experiments that would benefit from low beam energy or high repetition rate. And ideal experiments at the AS&T bunkers involve accelerator device testing, although any experiments you can think of that would use radiation shielded spaces are also welcome. Thank you.
Hi, my name's Todd Kubley. I'm representing the tandem Van de Graaff facility at BNL. We have two 14 million volt electrostatic tandems here on site. We can operate up to a terminal voltage of 14 million volts, which allows us to have energies of 1 MeV to 28 MeV protons and up to about 337 Me for gold. We can provide around 50 different ion species for any sort of implantation. Our beam spot size is around 2 millimeters to 30 millimeters, depending on the user. We can make a lot larger spot sizes if we need to. The facility does have 4 active beam lines. We have a active SEE testing a line that we use quite a bit. We also have one for ion implantations. Specifically, we have been doing a lot of silicon carbide implantations with that, but anything that needs to be implanted, we can. That actually has a temperature control on it, so we can go up to about 1,000 degrees C. We're also capable of running below 0 temperatures, so if you need to do an implantation cold or hot, we're able to do that. We can provide, since we're electrostatic, we provide a continuous beam. If you need to have pulse for some reason, we can pulse it down to a few microseconds. Because of our energy spread being so small, 1 part in 10 to the 4th, we are really good at doing detector calibrations. Next slide. So a lot of things we do are high energy implantations. This includes silicon carbide, like I talked about. It also includes superconducting materials are things we've worked on a lot. Anything that needs ions implanted into it, we're very skilled at doing that and very precise. We also are very good at doing detector calibration and single event effects testing. We have a dedicated line for that, which can hold multiple devices. We have multiple feed-throughs for whatever the user's designs need. And we're flexible enough to allow for any experiment. So with our 2 additional beam lines, we are able to put end stations on for whatever the user needs. And those, again, we have vacuum equipment, power supplies, feed-throughs, heaters, anything that you may need. we can probably have, and we can work with you to make sure that your experiment is successful.
Okay, I'm John Power. I'm the AWA group leader, so I'll talk about the Argonne Wakefield Accelerator. So you see we have 3 independently operable photoinjector beam lines, and each one can generate bunches independently, and then this large flexible experimental area in the middle. So looking at the beamline layout here, the main photoinjector beamline is the high charge dry wire photoinjector, makes 65 MeV electrons, and one of the unique features here is single bunches up to 100 nanocoulombs, bunch trains up to 600, and you'll see in a minute we also can go very low in charge. The second beamline is we call the witness hour photoinjector, and this is used for our 2-beam acceleration program, but it's an independent beamline in its own right. So if there's a need for a lower energy, a 14 MeV electron beam, this is also available. And then the last one, photoinjector, is the argon cathode test stand. This one's isolated from the rest of the facility. It's in the main bunker, but it's vacuum isolated from the main beam line. And we use that for cathode studies and diagnostic developments, and also the physics of high gradient breakdown. So then back to the facility layout, you see this large flexible experimental area in the middle. Essentially, each one of these green boxes is an experimental area. And our mode of operation, like Philippe mentioned, we have our own research program, but we also have a collaborator program. And each one of these green boxes is a test area where people can install experiments in more detail on the next page. And here it's highly reconfigurable. Our typical layout is we work closely with our collaborators on all the engineering and support. And a typical experimental run might be a 1 week worth of installation, which allows for installing and pumping down. And then the next week you would run the experiment. And we also have a 60 phase space manipulation program. One of the things is we have a big emphasis on student traineeship. So we're very familiar with, people who want to send students to work with us. And that top row, you see our recent graduates that are now almost all of them, I think, except one, are still employed accelerator physicists. And the bottom row are current graduate students at AWA. Lasers, our main laser is a photoinjector laser at 262 nanometers, but we have a variety of other lasers available too. And we do lots of, part of the 60 phase space manipulation is also laser control. So we do temporal shaping of the laser and bunch length control. Okay, next slide. I won't go over all the detail here. This is mostly just for reference. And of course, there's more details on the BeamNetUS page, but this is more detailed. That first drawing of the beamline layout was just gives you a quick glance at a block diagram level, but here's the actual layout. And you can see we have we call these zones 1 through 6. They're each vacuum isolated. So that allows us to be possibly running an experiment in one zone while we're installing an experiment in another. And there's a brief description of each one of these, what's in each one of these zones below here. As I mentioned in the beam, so we do make very high charge, 100 nanocoulomb beams, but we also go down to a picocoulomb. So we have 5 orders of magnitude capability on the different bunch charges we can deliver. It's a lot of variety in terms of charge, the laser pulse length and electron pulse length themselves, and the bunch trains. We can generate one bunch or a train of bunches. In the middle there is our own research focus, but I'll just skip that and mention again, the mode of operation is we have our own research program, but we also collaborate. So happy if somebody wants to reach out and work with us. That's it.
Thanks.
Yeah, so I'm Philippe. Again, I'll be describing this ITS and Leah for Yeni, who has a conflict and could not make it. So the ITS, or injector test stand, is one of the facilities in the Advanced Photon Source Complex. This was initially built to commission electron source for the Advanced Photon Source, APS. And it's a highly versatile setup where we usually have an RF gun that you can see on this EPIX model, and just a beamline that can do some diagnostics, spectrum, and also some compression through an alpha magnet. The system has a 30 megawatt klystron at the S-band frequency. This is a PFN modulator, so an older version. And it's all integrated in the EPIX control system. So again, everything can be remotely controlled and so on. It's also co-located to a 4 millijoule infrared laser, which can also provide about 500 microjoule of UV, and this can be used for photo emission. And over the years, it has supported R&D on RF gun, cathode. And I should say that it's mostly, although it's in the APS complex, it's mostly independent from APS. The only dependence is that the klystron is a spare klystron for APS. And so if it's needed, then we are not able to run. The parameters are shown in the table in blue, and this is for the nominal electron source we have right now, which is a thermoionic gun, so which generate about 3 MeV beam. Next slide, please. So this is an example of two type of research we conducted over the last few years. One was RF gun characterization. So if you have a gun and an electron source and you want to characterize it, this is a nice place to do so. This example, we actually characterized one of the LCLS-1 RF gun, which ended up being installed at APS eventually. So we could do all this RF conditioning, characterization, emittance measurement. All these diagnostics are available and interface to EPIX. And then on the right is a little bit more advanced research where we use this alpha magnet to compress the beam and to produce terahertz radiation, tunable terahertz radiation, and this was done in collaboration with an industrial partner. So next slide. So I'm going to shift gear to the LINAC extension area. So if you look at the diagram on the right, this shows you the injector chain of the advanced photon source, APS. So usually we use this thermoionic gun, which are called RG1 and RG2. And in the past, about 10 years ago or so, another gun was installed with a LINAC, and this is a photo emission gun, so as a PCG. And recently we upgraded the system, are in the process of recommissioning it. And so this LINAC allows us to generate beam and send it at the end of the beam instead of injecting into this booster and so on and so forth. We can go to this LIA, which is this LINAC extension area. And this is this picture. It's basically a long tunnel which has a beam line to test a component related to accelerator. Historically, was the place where the first demonstration of saturation of a SACFEL was done about 20 years ago. So LIA can take basically electron beam from the photo injector or from any of the thermionic source. And the LINAC also include a compressor chicane. So potentially it can do a couple of kiloamps peak current. These are the typical beam parameter. I think the energy is a bit lower than 500 MeV. It's between 4 and 460 MeV. And so in terms of operation, this is highly linked to APS operation. So basically, we can only send beam. Right now, we can only send beam in this area during machine study time. But the good thing is this is decoupled from the machine, meaning that we can do installation totally independent of IPS operation. Basically, we can enter anytime we want during IPS operation, but we can only run it when during slots allocated for machine study in IPS operation. Next slide. I think it's a couple of examples of ongoing research. I forgot to say that LIA is also co-located to two facilities. One is a laser room, and we hope next year or in 2 years from now to install another laser there. But it's also co-located to a high power RF test stand, which uses a solid state modulator, so quite stable. So there is right now a program in LIA using this RF test stand to test some of the S-band structure version of the CQ program. This is in collaboration with Slack. And another program, which is on the right, it's an R&D on radiation source. There was some program to reuse some ondulator from APS, some program with UCLA that were not completed, but these are examples of research that are possible. And again, I should say as a final point that both facility they benefit from the APS staff, which is one of the largest group in Argonne in terms of accelerator science and engineering support. So this is this is all I have for these two facilities.
All right. Hope you can hear me. My name is Jeroen van Tilborg. Together with Sam Barber, I'm the point of contact at the Bella Center at LBNL. So we are making available two facilities, very much related, called HTU and HTT. So I will present both of them. But really, what they share is that they are laser plasma accelerator facilities and beamlines, LPAs, and as you might know, that this means that a laser produces a very compact, very high gradient accelerator in a plasma. And because the plasma is easy to shape and make longer or denser or have substructure, it means this is really a highly tunable particle accelerator that can produce up to 500 MeV electron beams over millimeter to centimeter distances. So that's a unique capability within the BeamNetUS range of facilities. It also means we can everything is driven by femtosecond lasers, and there's all this femtosecond plasma dynamics. It also means that the electron beams are very short, femtoseconds, enabling very high peak currents, kiloamps. Go for
May I do
it.
Sambal instead of Mayo, please?
Oh, someone is not muted. All right. So yeah, these femtosecond electron beams then in turn can be used to make radiation pulses, light sources, X-rays, terahertz. Another unique feature is that the source of these particle beams and the radiation pulses are micron size. So there's a lot of potential there in high resolution imaging with electron beams, with X-rays, gamma rays, because of the point source nature of the source. Everything is synchronized, of course, to the laser. So a lot of experiments can be envisioned, as light source development, pump probe schemes, microelectronics studies, all at high resolution, both in space and in time. So yeah, so there's some typical beam parameters on the right, but let's go to the next slide. So I'll separate a little bit the two facilities, although they do have the common attributes at the bottom. So the HTU facility, in that drawing there on the bottom right, you see LPA target chamber. That's where the laser is focused, and that's where the 100 MeV type electron beams are produced from this point source. And what's unique about this beamline is that there's really a lot of electron beam manipulation, beam optics. There is already in the target chamber. You see that in the red inset. There is a very high gradient quadrupole triplet to collect and refocus the electron beam. Downstream of that, there are steering magnets. There's 4 dipole magnets organized in a chicane, so you can manipulate the time delay of the various electron energy slices. There's another tunable electromagnetic triplet. There's magnetic spectrometers. There is a 4-meter undulator called the VISO undulator, where we just published a PRL on free electron lasing, and so that's open for BeamNet to experiment on. And I think also interesting is there is a empty chamber, somewhat, I don't know if you can see the label, called E-beam diagnostic and application chamber. So in the middle of our beamline, we do have a chamber where over the years we've developed, again, light sources, CTR, micro undulators, microelectronics testing can be done there. So that's possible in this HTU beamline. Of course, this system, just like the next, are supported by all kinds of laser, plasma, electron beam, and radiation diagnostics. We have a control system that supports both LabVIEW and Python, and integration of AI ML workflows. And we have an expert staff available to help conduct the experiment and troubleshoot it with the mechanical and electrical support. All right, so then the next slide, please. So that was the HTU system. In the same experimental cave is also the HTT system. It's also a laser plasma accelerator. There, the unique capability is that the laser is split up in two arms, which are independently, they're synchronized, but they're independently controlled in terms of, pulse compression, energy, mode, beam size, focal length, parabola, etc. So we have a 70 terawatt and a 20 terawatt laser arm. They meet in the target chamber. I would say all the experiments to date have at least that drive laser make electron beams, and that really allows the other laser, the scatter laser, to do all kinds of experiments. For example, like I just said, scatter the electron beam and the scatter laser to make tunable monoenergetic gamma rays. But we've also done, of course, plasma manipulation with the second laser, or inducing shock waves in liquid or solid structure. So there's a lot of configurability there, a lot of options for experiments. Downstream, there is the electron beam diagnostics, and there's actually a very well shielded path through that shielding wall to a X-ray and gamma ray application table. Very recently, we also added, it's not on the website yet, a quadrupole in the target chamber for electron beam focusing experiments, such as microelectronics testing. So that's also set up in this facility as well. So I already went over the common attributes, so I'm gonna leave it at that. But I hope you understand what the HCDU and HTT have to offer. Thank you.
Thank you.
Okay, this is Wei, so I will represent HiRISE team members to introduce our facilities. HiRISE stands for the High Repetition Rate Electron Scattering Apparatus. The main features of our facility is we have ultra high bright electron source. Particularly, it is the RF accelerated photocathodes. The RF frequency is operating at VHF, which allows up to megahertz rep rate operation. It can produce up to 750 keV electron beams. And then our beam also equal with the laser systems. One is from with 515 nanometers for photocathode excitation, and for the sample target chamber experiment, we can have 1030 nanometers femtosecond fiber lasers up to 200 microjoule per pulse for the target experiment, and we can also further compress the pump laser beam from 300 femtoseconds to 10 femtoseconds for the experiment requires higher temporal resolution. And then our beam spot size can focus down to less than 50 micrometers diameters, and the energy spread with the low-level RF control feedback, we can reduce as low as 10 to minus 4. And the bunch charge, we can switch from 1 to 10 to 8 electron per pulse. Then next slide. Here here lists the outlines of our beam lines, and we have a dogleg and the straight beam lines for different purpose of the beam diagnostic experiments. We equal with a variety of focusing lengths and diagnostics, which allows I think this facility is particularly ideal for the AI machine learning adaptive control, hardware developments, and algorithm testing, since we can relatively flexible tune the beam and record the beam properties. And on the other hand, on the VHF gun, we have loader lot, which allows us to test different photocathode. So that means it's suitable to evaluate new photocathode materials, measure the quantum efficiencies, dark currents, and emittance, and etc. Our staff member includes down one machine learning experts, me for the ultra-fast spectroscopies, and Tianhuang Luan Ive expert, Gang Huang, FPGA precision controls, and of course our program lead and Qingji. So we are happy to support the experiments at HiRISE focus on the advanced accelerator projects, including machine learnings, photocathode, and also would like to support the target experiments, including the ultra-fast dynamics in a variety of materials. I would like to answer more questions in the Q&A section. Thank you.
Thank you.
Yeah, hey, good morning, everyone, or good afternoon to some of you. I'm Jonathan Jarvis. I'm the director of the Accelerator Research Division here at Fermilab, and I'm also over the so-called Fermilab Accelerator Science and Technology Facility, FAST. Just to give you a very high-level overview of who we are and what we do, FAST is roughly a $150 million scale facility. It's a very substantial accelerator facility, also uniquely capable and flexible. We have three primary instruments. We have an SRF LINAC that can produce 300 MeV electrons with very high intensity bunch trains. We have a brand new high intensity proton LINAC that we are about to commission. We're days away from getting our sign-offs for that. We've come out of a long shutdown, a 2-year shutdown, to prepare that device. And then we have a highly reconfigurable electron proton storage ring called IOTA, the Integral Optics Test Accelerator. At FAST, we see our mission as sort of pushing the boundaries, the frontier technologies and ideas that DOE and accelerator designers and operators of the future can use to pursue DOE science targets. For us, what that looks like being at Fermilab, the core of our program is aligned with Fermilab's sort of grand challenges related to the so-called intensity frontier. So this is how do you make very high intensity proton complexes, megawatt scale proton complexes? How do you evolve the complex that we have here at Fermilab? So we do a lot of things in intense beams, beam instabilities, nonlinear beam dynamics, etc. But we also have a broader program that's applicable to high energy physics' partners across the accelerator ecosystem. So these can be things that relate to beam cooling or light source technologies. And increasingly, we are developing at scale AI/ML techniques for optimizing and operating accelerators. And so, no one's going to let you do these very powerful but very new sort of autonomous operations techniques on billion-dollar scale proton facilities if you don't first de-risk those technologies in a high fidelity operations setting. And so that's really something that FAST is uniquely positioned to do. So our typical operations model is that we run six months on, 6 months off. Some 6 months are longer than others. We've had runs as long as 2 years, a year and a half, 6 months. It really varies based on the specific high impact science targets that were configured for at any given time. We have a standard proposal review process that we call the IOTA Scientific Committee that reviews feasibility, scheduling, resources, all of these sorts of things for any proposal, internal or external, that we want to execute at this facility. So that process has to dovetail and integrate with the BeamNetUS process, but that's entirely appropriate and effective. Next slide, please. Okay, so a closer look at our machines that we have, so-called IOTA storage ring, both protons and electrons, not at the same time because we inject in the same direction. So we switch back and forth, literally, swapping the leads to be able to run one or the other. We can do everything from very intense space charge dominated beams, so at the very high intensity scale, all the way down to single electrons. So that you wouldn't know it by looking at it, but IOTA can be a quantum instrument. We can put a single electron in the ring, leave it in there for hours at a time, and then we have very comprehensive, sophisticated diagnostics where, for example, we've recently done the world's first full 3D tracking of a single particle in a storage ring. It turns out this is a very powerful diagnostic for understanding your machine. So that gives you kind of a flavor of the breadth and the depth of what's happening. On the other side, our two LINACs, our proton LINAC, high intensity proton LINAC, so-called iota proton injector, and then the SRF fast LINAC. It hails back to the days of the International Linear Collider. We started as an ILC test facility. You can see from the picture on the right there that we have a very, very long accelerator tunnel. We maintain the capability to upgrade with up to 5 more cryomodules and GeV class beams. But for right now, it's a single cryomodule 300 MeV system, but uniquely we can do a very high intensity bunch train. So this can be up to say 1,000 pulses spaced at 3 megahertz with multiple nanocoulombs per pulse. So this is a very unique intense beam capability that we have from those ILC type days. We also have a high brightness photo injector and a low energy test area where we can do experiments anywhere from 5 up to 50 MeV. And then we're increasingly building out a high energy beamline test area where in the future we can do sort of beam light interaction sort of work, or even potentially sample irradiation. We did receive lots of interest or inquiries about whether or not that was a capability we had. It's something we're exploring, and we think there are low friction ways to get there. As you can see from the specialties list, it's all over the map. It's everything from very intense beam dynamics and technologies related to intense beam dynamics, all the way to AI for accelerators. And then we have some laser specialists on site and a couple of laser labs that we use to support the facility. So I would say as punctuation that the ideal experiment is one that dovetails with our existing mission in high intensity beam physics. But in any R&D organization, new people, new ideas, these are the seeds for the future. This is what makes an R&D program robust. And so in bold, most welcome. Any new ideas, no ideas too crazy. We'll let you know if it's too crazy or if it doesn't work for us. But we're very happy to welcome you to FAST and to talk. Thanks.
Thank you.
Hi, good morning, everyone. My name is Ivan Rajkovic, and I hope you can hear me. I am a user coordinator at FAST facility at SLAC National Accelerator Laboratory, and this is one of the 2 facilities that are available from SLAC at BeamNetUS. So FAST provides beams that are optimized for next generation of plasma wake-field acceleration experiments, but not only for those kind of experiments, because we also had successful experiments with coherent radiation generation techniques. We are also, as everybody else these days, using machine learning to control the accelerator and to use it for the diagnostic of our beam. And we're also probing the strong field QED with an E-beam laser collision. So what is unique about FAST is that we can provide beams with 10 GeV energy electrons. The repetition rate is 10 Hertz, and we can have them around 2 nanocoulombs per pulse. The spot size at our interaction area is around 20 micrometers. And what is important also to mention that these are some typical beam parameters, but we have a few different beam capabilities where we can have either a short beam, long beam, or we can also have a single bunch and 2 bunch. So meaning that these 2 nanocoulombs can be split into 2 bunches that will come close after another to the interaction area, and we can either have them starting from the cathode or just making them with a notch collimator just in front of our experimental area. So, and if you go to the next slide, we can show. So here we can see a few of the experiments that are happening at FAST. So first of all, FAST is a user facility, and we have a strong user program. So you can, apart from the BeamNetUS, you can also have a proposal that will go for multiple years. And some of the results of these proposals are shown here. So apart from the acceleration with plasma wake field, we can also use that wake field as a thin lens. If we just excite one part of it with a laser, we can use that thin lens to focus our beams. And apart from the plasma for focusing, we've also shown that we can use a multiple of thin aluminum foils for focusing the beam, where the effect of multiple foils is much stronger than the effect of one foil with a single thickness. So from the correct capabilities of our facility for plasma acceleration, we do have 3 different plasma sources. We can either use lithium oven, we have gas jets, so we can have a very just one part, very short path of the e-beam going through the gas jet, or we can have a static field where our whole experimental chamber is filled with a gas, and we can have multiple sources of gases, multiple choices of gas. We can use hydrogen, helium, argon, or mixture of these gases. And as I said, we can use it for acceleration or for plasma lens. So when we are not, apart from the plasma wake field, yes, with the high field physics, we can use this term GeV, very high intensity and ultra short electron pulses to interact with laser, to interact with solids and have different effects. What is also important is that we do have a TISEF laser, which is synchronized to our electron beam, and we can use it either as a pump laser to pre-ionize plasma or to interact with the e-beam, or we can use it as a probe laser to basically probe the effects of our experiments. So we have staff that are experts in both accelerator method and in ultrafast lasers. So if you have any questions about the experiments that we can do, any questions about your proposal that you want to submit, please contact me, and I can connect you with a fastest staff, or if you know whom from the fastest staff you would like to contact, you can also contact them directly. So that would be all. Thank you.
Thank you. Okay, my name is Emma Snively, and I am the operations manager for NLCTA, and I'm also the deputy chair for BeamNetUS this year. NLCTA has a historic focus on X-band accelerator technology. The bunker was originally designed to support up to a 1 GeV electron beam. These days, we use that accelerator enclosure for multiple distinct test areas. So in one of those areas, we have the XTA beam line. This has a standalone photo injector and LINAC that gets the beam up to 75 MeV. So typical experiments that we do on XTA include detector characterization, sample irradiation. We're also able to mount an X-band accelerator structure on that beam line and test it with injected beam. For a device under test, we can mount it in air at the end of the beam line after a beryllium window, or we can mount it in vacuum in a sample chamber downstream. And then we also have Ti-sapphire laser that we use for our photo injector. We can split that and send it to the sample chamber at the end as well. So one of the things I want to highlight about NLCTA is that we have not only this X-band test accelerator, but also these other test areas with different unique capabilities. So we can do high power RF testing at S-band and at X-band in these distinct test areas. This year, we will have X-band plumbed into a cryostat that can get down to 4 Kelvin. And then we can also do RF processing measurements and testing at S-band. And then to highlight these test areas, one of the new features this year is going to be a 5 Tesla solenoid. So this is going to be set up with high power RF at S-band. So we can test cavities in high external magnetic fields. And eventually, a couple of years down the road, we're looking to transition this to also being able to test at L-band. And then, as I said, we have cryo testing capabilities with high power RF. We're currently set up, or we will be set up to do this at X-band, and then we can also switch over to doing this at S-band. So throughout the facility, we have experiments going to look at controls and diagnostics, testing new platforms for low-level RF. And we're also expanding in the area of ML testing and taking advantage of the ease of access to the facility and how quickly we can turn around, kind of shutting off tweaking controls and diagnostics, going into the accelerator housing to make changes to the hardware, and then resuming operations. So there's a lot of flexibility with this facility. Thanks. Matt.
Hey folks, I'm here. Sorry about the delay. So yeah, my name is Matt Pelker. Hope you can hear me. and I manage the upgraded injector test facility, kind of a spicy name there, at Jefferson Lab. So UITF is a SRF LINAC. It provides CW spin polarized electron beams, and I think that's our niche within the BeamNet community. We have a 200 kilovolt spin polarized photo gun. Beam polarization is about 80%, and a Wien filter to rotate the spin out of plane. There are polarimeters there, of course, to measure the polarization. We have a brand new cryo module that we installed. It's a niobium tin coated cryo module, and it can provide up to about 8 MeV. And happy to say it functions quite well, very stable at that energy. Right now, our shielding, the concrete we have around the facility is such that we can only accelerate up to 100 nanoamps average current at 8 MeV. The shielding can be augmented, but we'll need some money for that. Right now, we make an electron bunch from the gun at every RF cycle of our cryo module, and that's 1497 megahertz. We can modify the drive laser to provide subharmonic beams. So mostly what we do is you can see a student there in the bottom photograph, Ji Li. She helped evaluate whether or not an electron beam can get rid of contamination from our drinking water. So PFAS chemicals and 1,4-dioxane are common things. And she did a great job. So it is a wonderful place for students to do their work. And we found indeed that the electron beam can be pretty effective at getting rid of contaminants. The next thing we're gearing up for right now is to make polarized hydrogen targets for our physics program at CBAF. So like some of the speakers mentioned, we have our own program, and then when it makes sense, we can augment that program with people from the outside. And so one of the groups from the outside is interested in enhancing the fusion reaction in a tokamak, and we would do that by polarizing deuterium, and then the deuterium pellets could be injected into the fusion reactor. So that's a nice synergy. Right now, we have never performed an experiment that I would call like a physics experiment with polarized beam. And I look forward to anyone with proposals that have ideas for that. You can go to the next slide, please. So this injector, we call it an injector because it's modeled after the CBAF injector. CBAF is our big nuclear physics machine just a quarter mile away. I don't have it listed, but we test photocathodes here too, and we've worked with the DOE to come up with people who can manufacture high polarization photocathodes, and that's been effective. There you see the cryo module, and on the left side is where we do our irradiation of things. So we're adding a third beam line there on the left side as we speak. So that's about it. I look forward to any questions.
Great, thank you. And thank you to all of the presenters for all of these facilities. So I think we're now gonna switch over to the Q&A.
Yes, and I think Philippe is gonna lead that.
Yeah, so I think we can take any question. There was a question from earlier, maybe that we should reply to, I think from Chen Kung Huang. Are you still here? Or?
Yeah, can you hear me?
Yes.
Okay.
Yes, go.
So I just wondering regarding the C funding scenario, if we are proposing some idea, but we want to seek further funding through experimental demonstration in this kind of scenario, if the proposal to the BeamNet is reviewed at the same standard criteria.
Maybe let me go a little bit from the beginning. So the BeamNetUS is what provides basically what I call seed funding to check the sanity of an idea experimentally at one of the user facility. And the hope is eventually, if you would get the result you are expecting or the initial demo, then you can go to a funding agency for you know, let's say a more multi-year or so funding source. So that's what I meant during my talk. Do I answer a question or?
If I understand, that means that most of the BeamNet experiment will be proof of principle type.
Yes,
And
exactly.
you're welcoming this kind of
Yes.
experiment. Okay.
And you know, the idea is that eventually, if you write a proposal to another funding agency, including this preliminary result would enhance your chance or of your proposal. So that's the idea. Yeah.
Yeah. So a related question. So with that kind of scenario, because we also have to prepare the actual physics proposal for the funding agency. And now we also have to catch the deadline for this one, which is the end of next month.
Yep.
So I'm just wondering if we can kind of coordinate with different facility to allow some sort of a late submission.
I think our goal initially is to move the window for the submission window earlier to make sure that uh, the experiment could be performed anytime during the upcoming fiscal year. But so far, this is only our second year, and we just got really organized with the structure this year. So this is why we are still a bit shifted compared to the other calls.
Okay, thanks.
You're welcome.
We have a question from Chung Wang.
Well, yeah, Philippe. So two questions, sort of related. The first one is, I noticed 12 facilities. Does that mean you have a limit number awards each year, like a 12 or less or more, or it's funding dependent? That's the first question. Second is, do we have a limit how many proposals can submit it by a single institute? Thank you.
So let's say the first question, yes, the idea is that one proposal per facility will be funded if the proposal are strong enough and well reviewed, of course. So the idea is that we will have well, actually, maybe I should back off. I think we have 11 facilities this year because I think ATF is not accepting proposal. But anyway, so one proposal per facility will be granted beam time, assuming it reviews well. So the competition is really at the level of proposal applying for beam time at a given facility, basically. Now for the second question, and I think a PI can propose several proposals. Last year, I believe we had such a case, but maybe Lotte or Emma can correct me.
I actually want to speak up about the first question as well. So I think it varies by facility, and some facilities have enough availability to support more than one experiment. So there may be more than one proposal may be accepted per facility. Then yeah, I don't believe that there's any restriction on an institution submitting more than one application to a single facility or to multiple facilities.
Yeah, okay. Yeah, I don't think there is. So good. Yeah, good point for the first one. Yeah.
Yeah, I think it's probably from the user side of things, I think it's probably unlikely that the same user would get awarded 2 beam times at the same facility. I think that is probably not going to be likely, but indeed the user could submit proposals to multiple facilities.
Got it. Thank you.
I don't see any more questions at the moment.
Hey Lottie, I got a quick question.
Go ahead, Kyle.
Yeah, so I think I probably know the answer to this, but is there any possibility for submitting, say, a proposal for like a single proposal to two facilities, say like two short beam times to two facilities to compare results at, different types of beams?
I think so, yeah. Mm-hmm.
Okay, so you could do like a LPA facility and then like a more of a conventional RF facility.
Yeah, yeah. And then, I mean, ultimately, it is up to the PRP.
Right.
I should spell out that acronym, Proposal Review Panel, to decide whether they want to award both of those. There's no requirement for them to accept like tied experiments like this. But if there's a strong scientific case that you all present, then yeah, it's possible that they would be accepted.
Cool. Okay. Would that be a single proposal then, or would that be two separate?
That would be two separate. Yeah.
Okay, cool.
I guess you
All right.
could link to the other one, right? If you're like
Sure.
somehow in your text, in your narrative, you could point out that you have a partnering proposal or something like that you're submitting as well.
Sure. Okay. Thank you.
Any more questions for the big room? If not, we had planned to go into some breakouts that are split up into the different institutions with facilities. So you're welcome to select one of those breakouts if you have questions that you want to discuss in a smaller setting with the facility staff. You're welcome to stay in the main room. I will hang around here if you have more general questions about the proposal process. And then if you have no questions to discuss and you're going to sign off, then we say thank you for joining today, and we look forward to receiving your proposals. And you can reach out anytime following this, of course, in case of questions.